This is part one of a multiple part series on reaction mechanisms. That is literally the sorts of collisions involved between molecules that are reacting with one another. And it's a particularly useful consideration, the mechanism, when one is studying kinetics, chemical kinetics, because of course kinetics is about the speed of reactions, and fundamentally that speed is determined by the number and types of collisions that have to occur between reacting molecules and the subsequent bonds that have to be broken to achieve what's called the activated complex. And that in turn determines what's called activation energy, and that fundamentally determines the speed of the reaction. Now, very few reactions actually occur in a single collision. One such example is the reaction between hydrogen and iodine that produces two molecules of hydrogen iodide. This would happen in one simple collision if the hydrogen molecule, H2 represented here, happened to collide with sufficient activation energy in the correct orientation to the iodine molecule to break the covalent bonds in the hydrogen and break the covalent bonds in the iodine and allow formation of new covalent bonds between the hydrogen and iodide itself. However, the particular reaction that I've drawn here does not occur in a single collision. Instead, it occurs in what are called fundamental steps, in particular two fundamental steps in this mechanism. Now, a fundamental step is a fancy word for, or fancy phrase I should say, for a collision, an actual collision that is necessitated to further the reaction's progress. And so what really happens in this reaction here is that a hydrogen molecule, 1, will collide with an iodine chloride molecule and will produce hydrogen iodide and hydrogen chloride. And you may be saying, well, what is going on here? Hydrogen iodide has absolutely no role in the reaction. And that's true. It is what is called an intermediate. And an intermediate, by definition, is a molecule that is produced in one of the fundamental steps and then immediately consumed in an ensuing fundamental step. And of course, the second step here requires that hydrogen iodide collides with iodine chloride. So hydrogen iodide must be an intermediate because it is produced in the first collision, the first fundamental step, but immediately consumed in the second fundamental step in its collision with iodine chloride. And so of course that's why it appears as neither a reactant nor a product in the overall reaction. Now, what we see here is stoichiometrically these two steps do give us the net reaction that we're talking about. Namely, we consume a hydrogen in the first collision, and we consume two iodine chlorides, one in each of the two collisions or fundamental steps. And the net result is producing an iodine molecule and two hydrogen chloride molecules. The hydrogen iodide itself, as an intermediate, does not have any place stoichiometrically in the overall reaction. So this is key because any proposed mechanism for a reaction must be stoichiometrically consistent with the overall reaction. You can't have molecules in your collisions that are not in the overall reaction unless of course they are intermediates and therefore cancel from the two steps. Now, a little more vocabulary here in this mechanism. Because the first step is slow, it takes a long time for there to be hydrogen iodide produced that can be consumed in the next step. This next step is much faster. And so we call the slowest step of any mechanism the rate determining step. The rate determining step is always the slowest step in the mechanism. And it's called the rate determining step because literally it determines how fast the reaction can run. Now let me give you an analogy. let's pretend that there's an assembly line in a factory, and that the assembly line moves each item down the belt, the conveyor belt, and then stops in front of each worker for a period of time, and then continues moving on after all the workers in the line have done their job. Well, if it were, say, a car factory, and I do know that some assembly lines move constantly and the workers have to run along to do whatever it is they're trying to do, but in our imaginary assembly line, when things stop in front of all the workers, let's say that this worker here has a really busy job to fulfill. They have to do 2 or 3 different things to the item being manufactured and then step back before the assembly line can move on. On the other hand, this guy's got a really cush job in the manufacturing process and does one simple modification of the item being manufactured, sits down, relaxes, looks at his watch, checks the paper maybe for the assembly line to move on. And then eventually you'll notice that whichever worker takes the longest determines the rate for the entire production process, because things can't move forward until the slowest worker does their job. So the rate determining step for any mechanism is the slowest of the collisions, and it's usually slowest because it has the highest activation energy. The bonds being broken, and in this case between hydrogen atoms, are usually stronger than the bonds being broken in the other collision. In this case, a hydrogen iodide bond has less energy than a hydrogen-hydrogen covalent bond. And so consequently, these molecules must have a higher activation energy when they collide to successfully collide and break the bonds. And on the other hand, the faster reaction does not need as much activation energy. So at the same temperature, more of these molecules can successfully collide rapidly, and fewer of these can. Now, the most important understanding to take away from these mechanisms is that the rate determining step determines the rate law. And in this case, because a hydrogen collides with an iodine chloride, if you were to double the concentration of these hydrogen molecules, they'd be twice as likely to collide with the iodine chlorides. That means, of course, that there would be twice as many collisions, twice as many unsuccessful ones, but also twice as many successful collisions. And it's those successful collisions that determine rate. So because there's only one molecule of hydrogen involved in this collision, by doubling its concentration, you double the rate, because you double the number of successful collisions. And so that means that the order of hydrogen is 1. It's the same as the number of molecules in the rate determining step. The same could be said of iodine chloride, that if you doubled its concentration, it too would be twice as likely to collide with hydrogen, and therefore it also must be first order. The only time I'd see a second order reactant would be if 2 of the molecules of the same kind were colliding with each other. Now here, if you doubled both concentrations, the reason the rate would quadruple is you are increasing the chances of collisions 4-fold if both things doing the colliding were doubled in concentration. So yes, by knowing the mechanism, you can in fact determine what the rate law for the entire reaction must be, because the rate law of the rate determining step is always consistent with the rate law of the reaction, and that's because the rate determining step determines rate of the reaction. So it's no wonder that their rate laws would be identical. So yes, even though this reaction involves a collision, or apparent collision just from the net stoichiometry of a hydrogen with 2 iodine chlorides, in fact that is not what happens. We have 2 separate what are called bimolecular collisions. Bimolecular collisions involve two molecules colliding. However, in many mechanisms, you'll often see unimolecular collisions, where a single reacting molecule has to collide, not with another molecule necessarily. It can be any other molecule, not a specific one, or it could even be the sides of the container. Unimolecular collisions are usually what you see when a single molecule has to be broken in the activated complex. Some covalent bond within it has to be broken. And that doesn't involve a collision necessarily with another molecule, it's a collision with anything. What you will never see, virtually ever, in mechanisms, and it's something to avoid if you are proposing a possible mechanism for reaction, is what are called termolecular collisions. Those are collisions that would occur if three separate molecules were to converge and collide with one another in space in exactly the right orientation with just the right activation energy for a successful collision. And the chances of that are so unlikely, very few mechanisms operate by any form with termolecular collisions. And even if they did, they would be very slow reactions because the likelihood of successful collisions would be very small. So the important vocabulary we're going to work with on successive videos are, of course, the fundamental steps, the actual collisions that a reaction follows in its mechanism, and of course molecules such as hydrogen iodide that are intermediates. And we're going to focus on the orders being related to the actual numbers of molecules involved in the rate determining step. And that rate determining step can be used to write the rate law, not only for the rate determining step, but also for the entire reaction. And typically speaking, we are going to limit ourselves to only mechanistic steps that include bimolecular or unimolecular collisions.